I will also check with Eindhoven just to be sure that this is fine. Okay, now returning back to division, there are two things here again. I have to find a function which is a good function, and good function does not mean a function which is giving you the solution. It's a function which is giving me the solution with simple iteration. And second, I have to find an initial approximation. If I start from here, it will take me longer to converge to the root. If I start from here, I'll get closer and faster. Then the initial approximation is very important. Now, if I am doing the reciprocal by convergence, I can use as function 1 over x minus d. You see, d is part of the function. Otherwise, there is no link with my problem. It has to be there all the time, right? And then I'm computing now the derivative of that, and this is my iteration. What you see now is that in each iteration I have 2 multiplications and 1 complementation, and there is some kind of dependency here. Then this multiplication with this and this with this are one after the other. Now again, playing the same trick with having the error at iteration I can determine the error at iteration I plus 1, and again it's quadratic. And also this one, it's going towards a solution in a quadratic way. Now the question is how to do the approximation for the initial point. Approximation can only be done when I know the dynamic range. And for this dynamic range, you know, which will bring me between, 1 and 2, the result, I can say my best guess is 1.5. That's okay. You'll remember this class. I'm pretty sure you'll remember Newton-Raphson. Then now, because my solution can be anywhere between 1 and 2, starting between 0.5 and 1, I can make the choice and I say it's 1.5. I'm in between in the middle of the domain. Now, this is simple, but it's not taking into consideration the value of d. I can also make that choice, which will require some calculation. Don't get scared about this, because those are offline calculations. The only online calculation is I'm shifting this and I'm making here a subtraction. And that one, it's a better one. Then I invested a bit at the beginning, but I will get a better evolution towards the result. Now, I can also choose another function, because this is not the only function. And that function will give me another recurrence. What you see here is that I have only one iteration which is going on, not 2 iterations going on in parallel, as it is the case for convergence, for this kind of repeated multiplication. Now, we are kind of revisiting the story of division by repeated multiplications, and we are trying to see how can we speed it up. And in here it's an example, there are, I want 64-bit numbers, I have a 3 nanosecond multiplier, which is from the Stone Age. Today, it's very slow, and the time will be about 33 nanoseconds. Now, the question is, how can I do better job? Better job can I do in different ways. I can do less iterations, which means I start somehow, I jump some stages in the iteration, I can also do approximation. Then I can do calculations which are not precise but are approximative. Or I can use faster multipliers. And let us look at them one at a time. Now, I mentioned that in the previous case, in the previous discussion when we were talking about that. You saw that each and every iteration I was doubling the number of bits of precision, which was discussed in getting closer to 1. Now what I can do is I can do an approximation in the beginning in this way. You know, I want to compute 1 over d. Now for this 1 over d, I can use some bits from d, a number of them, and use them as an address into a lookup table. Then, let's say I'm using 3 bits. If I'm using 3 bits, I have 8 locations in the lookup table. It's not that large. I can use more bits. Now, before starting the iteration, what I will do is I will take those bits. I will get from the lookup table the approximation, and then I will start with this, the iteration further, you know, the multiplications. This will bring me to a point where doubling the precision will really make sense. Okay? Now, here you have an example on how you compute that, you know. If this is the value, 1 over d is between those, and then you compute the input of that. That's, you know, very important. Now, it's fundamental when you want to do the implementation, but conceptually speaking, it's not important. Now, this will bring you to that kind of approach. Remember, in a normal multiplication base, you are converging nicely to q into 1, and you can get closer to 1 minus unit in last position. Now, because in my first lookup table, I get an approximation of that, you know, the convergency now will be from the top. I'll have this jump, and then I will get closer to the value. But somehow, this will eat a number of iterations at the beginning, which are not very effective. The ones when I'm doubling it slow. Let's say, if I want to compute 64 bits, and I have a lookup table which is giving me 16 bits of precision, then I have to go to in 2 iterations, I'm done. Then it's getting very effective. Now, I can also, you know, doesn't matter the road as long as I get to the destination. That's one very good principle in engineering and in science. I will take the one which is the easiest one. And I can also converge to the solution in this way, you know, by oscillation. And this will actually be useful because instead of doing full calculations, I will do truncated calculation, which is somehow like this. You know, in an iteration, in a precise iteration, I would move from this position to this position. You know? I'm getting more precision. In an approximate iteration, I'm moving from here, here. There is a kind of error between them. But this will allow me to do this iteration faster. In which sense? That I am starting with multiplications where precision is smaller at the beginning. Then I will do some kind of things like that. And eventually, in the last iteration, I'm using full precision. Then I have a 64-bit multiplier. And in the last iteration, I'll use it in order to do the final calculations. But in the initial, you know, let's say in the initial step, I make, you know, a lookup. And then I have iterations which are using more and more precision. I start with 9 bits, 17, 32, and I get to this. Now, there is a trick here. If I design a 64 by 64 bit multiplier, a 9 by 9, a 1732, then it's not good. because I will have a lot of multipliers which I'm not really using. Then I have to have this multiplier designed in such a way that I can use it with variable precision. Then it will be a bit of overhead in it. But from the other point of view, it will be faster at the beginning, and it will also consume less power. And will bring me to the solution, and this is very important to get to the solution. Now, this is a picture which you have to treat it in a kind of different way. This is telling you that, essentially speaking, you can use one multiplier and not three. Those are not three multipliers. This is one and the same multiplier in different stages of the calculation. Somehow in the book it's not clear that. Then this is telling that with a proper scheduling, you can use one multiplier, which is pipeline with two stages, in order to do those two iterations in parallel without any trouble. Then what you do first, you compute di or xi. Then you inject it here. Here it's empty. After one cycle, this will get in the final stage, and you can inject now the multiplication of z. When this is ready, then this will go in for output. You can now go for the next multiplication. Di plus 1, xi plus 1. Okay? And now this is moving in this way, and by the fact that the equations are in this way, you can share the hardware. Then the apparent performance is like you have two multipliers, but you only have one. Except for the small latency of one stage when nothing is coming out, for the rest of the iterations, the performance is like where you have two multipliers. This will not function for Newton-Raphson. You cannot do that for Newton-Raphson. For Newton-Raphson, you need two multipliers to do business. Okay. Now, I think I'm done for this. This is on how to do the lookup table and things like that. And I would say that we kind of covered the integer arithmetic. And we arrived to the end of the core part of the course. Then, thus far, we know how to represent numbers, and we know how to do all the basic operations. Then we can do whatever we want. We also know how to approximate functions. Then, all the things that we discussed in the previous hour and now can apply for other functions. I can use similar things to evaluate trigonometric functions or logarithm or other kind of stuff. We will not have the time to get into that. This is later on in the book. Now, the next step is to look a bit on floating point representation, because thus far we are only dealing with integers. Unfortunately, in real life and in programs, we have to deal with floating point numbers as well. And programmers do have a very bad habit. They write float without any pain. You know, when you type int or float, it's not such a big difference, right? For the processor, it's a big time difference. Then next time when you think about making a variable float or integer, think twice. Because what is happening is that all the things that you know for integers will be utilized plus more. And in floating point representation, things are getting more complicated. Okay. The need for the floating point representation relates to the fact that with a fixed point representation, you cannot cover a good dynamic range. From the point of view of the hardware, fixed point representation, it's like integers. Remember I said there is a decimal point only in my mind. And if I have a budget, let's say I have numbers and I have fixed point numbers, and I am allocating the same amount of bits for integer and for fractionals. Now, I have a problem with that because sometimes I need more bits on the integer part, sometimes I need more bits on the fractional part. You know, for those two numbers, if I make the square of them, in both cases, I will not be able to represent, because this will be too large and this will be too small. And the floating point principle is you do the calculation and you kind of move this point depending on what you want. But when you move the point, you have to remember that you move the point. And this is let's say, the fundamental of a representation, which adds a new aspect in the number. You have the value of the number, and you have the position of the decimal or the point. Then you have a value which is the fractional part or the significant, and then you have another one which is the exponent. And the exponent will tell you where this point is. Now you can represent this number also in this way, but the power of the representation is due to the fact that by moving the point, I actually change the exponent, and I am utilizing my bits in the best way. Like in this way, when I'm doing squaring, what I have to do is I have to move it in this way, then to borrow these bits in the integer part. While in here, I have to move the decimal point in this way to move bits in the fractional part. Now, then, a floating point number is represented like a significant or a mantissa. There are different kind of terminologies, which has a sign, and an exponent, which also has a sign. Then in a floating point number, I have two signs. The sign of the significant, which is actually the sign of the number, and the sign of the exponent, which is telling me where the position is, okay? Positive or negative. Now, I should not make confusion between those. And when I'm doing operation on that kind of numbers, you can already guess that I have a unit which is taking care of the significant. Let's say when I'm adding two numbers, I have to add the significance, and I also have to take care of the exponent. But I'm not adding the exponents. I'm just adding the significant, and maybe if the result requires, I'll also play a bit on the exponents. If I do multiplication, then it's simple. I add the exponents and I multiply the significance. Then what I'm doing now, in order to do floating point arithmetic, I'm building upon what I have. Then integer arithmetic, and augmented with other units which take care of the exponent and take care of what we call the normalization. Because this significant has to follow some kind of standards. And that was a problem for a long time. Okay, this is the representation of these two numbers now, you see, and this is what is called normalized representation. Then you always represent the number like 1 point something. Then you will move the decimal point in such a way that it gets after the first one, and then you see the implication on the exponent. And this is for the other one. Now, before we all agreed on how things have to be done, there were a lot of standards in floating point. of them were kind of representing the numbers in this way, but somehow different. You know IEEE, right? It's our organization. After a lot of effort, IEEE managed to standardize the floating point representation, and now, you know, if you make a floating point unit, it has to be IEEE compliant. Then, the number in floating point format will span over a word in my architecture, being it 32 bits or 64 bits or whatever. From that word, I take a piece, which is 1 bit, and I use it for the sign. And this is the sign of the number. It's positive or negative. And that's the first bit. Then I have an exponent. Then a couple of the bits I use for the dynamic range of the exponent. And the exponent in IEEE standard is represented in a biased mode. If you remember, long time ago, I was talking about biased representation of negative numbers. It was in prehistory, right? Now, we are using it for the exponent. The more bits I put here, the larger the dynamic range. But if I put more, I'm eating from the significant. And in the significant, I am now representing what is called the mantissa, or the value of the number multiplied with the exponent. What we have in IEEE, and by the way, this is radix 2 representation, but there are processors today which do have radix 10 floating point. They have radix 10 units, and this is mostly for banking. Because when you do conversion from radix 2 to radix 10, you may lose some cents, and then the bank or the client may get rich. Most of the time the bank is losing money, and they don't want to do that. Now, the significant is done, you have a number of bits, and that number of bits is utilized, but it's utilized in a kind of smart way. It's normalized, which means that the significant is always 1 point something. Then I'm adapting the exponent in such a way that the value, it's okay. That one, I'm not storing. That one, it's only in my mind, and actually I have to use it in calculations later on. Then when I get the value from the register, and I really want to use it, I have to pad this one. Because even though it's 1 point whatever, it will be only whatever after the point there. The one is implied. Now, this representation, it's covering a larger dynamic range, but it's covering the dynamic range in a non-uniform way. And there are a couple of issues. You know, I can represent positive and negative numbers. This is from the sign. Now, in the positive number, but also in the negative number, things are the same. There is a moment when my capabilities are finishing. Then I cannot represent numbers which are larger than something. This is normal. But what is kind of strange now is that I cannot get closer to 0 than something. Then around 0, there is an area where I cannot represent numbers. The reason for that is actually the normalization of the significant. Because I'm making the significant always normalized, it is 1 point something times 2 at power minus maximum. Then smaller than that, I don't have. We were talking about overflow when doing addition, but we never said underflow. Then for floating point numbers, I may get a result which is not representable, which is between the minimum number and 0. 0, I am able to represent, but it's a kind of convention. But numbers around 0, I cannot represent. And there is more than that. Due to this trick with the borrowing of resolution and magnitude, the uniformity of representation, which was true in the integers, is not true here. Then closer to the minimum, I have denser. Then I can sample numbers which are better accuracy. Closer to the maximum is sparser. Then some numbers I cannot represent, which means that some numbers I have to evaluate or to have an imprecise representation. Then I already see one thing which we didn't discuss yet, errors. Then I'm computing and I live with errors. In integer arithmetic, we had no errors. We are assuming that the hardware is perfect. But I'm not talking about that kind of errors. I'm talking about representation errors. The numbers cannot be represented. Then I am in a scene from the beginning. I want to do some kind of calculation, and because I cannot represent the operands, I have an error. From the, it's native. And when I'm doing calculations, things will actually evolve. And you will see that next week, Monday, we'll talk a bit about that too. Okay. Okay, that's the story about standards, and these are the two basic standards, which is short and long. And that's the way the budget, the big budget is split. Then I have 32 bits or 64 bits, and you see, depending on the format, I have more bits for the exponent, which means I have larger dynamic range for this, and I also have more bits for the significand, which will give me, better accuracy. And this is the way I understand the numbers. Okay? Then we know the part, then we know, let's look on this one short, because the other one is similar. Then I have 32 bits, 23 are for the significant, but remember the one which I'm not storing is there, and it's assumed to be there. I have 8 bits for the exponent, bias is 127. Now, as I said, there is no zero, because if I compute zero in the way which is according to the calculation, will not give me that. And I have two kind of conventions. If the exponent plus bias is 0, which is actually not 0 because it's 2 at minus 127, and the fractional part is 0, I have a 0. According to the calculation of the number in floating point, this is not a 0, but this is a convention. If the exponent plus bias is 0, and the fractional number is not 0, I have denormalized numbers, which means I have a way to signal that I am getting close to 0 with my calculation. I cannot normalize them, but there is still some information there. Then I am somewhere in this area, and I will try to represent some numbers there. But the fact that the exponent plus bias is 0 will tell me that I am in that situation, because otherwise this is not okay. Now, and those numbers are representing numbers now. I don't put the 1 here. I know that they are not normalized. And this will be the value, as much as I can. In the same way, I have some kind of convention for the other end of the domain, which is the infinity. If the exponent plus bias, it's the maximum value, which is not infinity, but it's the maximum value, and the fractional part is 0, then this is considered to be infinity. If the fractional part is not 0, this is considered to be not a number. Okay. Now, what is not a number? Division by 0, for example. Square root of a negative number. Then those are conventions. And you have to implement them in hardware. And you have to signal to the processor. Then if you look at an adder, to a normal adder, you have the carry and the sign and the 0. In the same way here, you have to have some kind of bits which are signaling that kind of situations. Now, for ordinary numbers, you actually have this kind of dynamic range for the exponent and and then you see this is minimum and maximum numbers. And if you go to 64 bits, you see you have a huge increase in precision. The philosophy is the same. Now, before having the IEEE standard, those were different. And everybody, each company had a different way to deal with that, and IBM was pushing for something, DEC was pushing for something, and you know, programs which are running okay on an architecture could not run on another one. And that was solved. Okay. Okay, now in here, okay, this we discussed, okay, about encoding and how I represent numbers and things. Then I am allowing to do calculations with denormalized, but in certain conditions, and I have to be aware that I'm doing that. Because otherwise, things will get under control. I don't have to say anything here, right? We discussed about that. You see that I have plus 0 and minus 0, but that's not a problem. There are also some kind of extended formats, which are also okay for IEEE, and they do not have hardware support. And if you go for that kind of formats, you actually are doing applications which require very huge numbers. And what you rely on are kind of emulation libraries. Then you will have your engine, which can do in 64 bits, for example, and then you will do a kind of emulation in here. That will be slow, but it's still standardized and things are working fine. Now, in this system, we have our friends from integer calculation, which are addition, multiplication, and division. And we have another operation, which is square root. And there are conditions for, compliance with the standard, which will then when you make a functional unit for floating point, you actually have to run on it some kind of benchmarks. And if the results are according to the benchmarks, then it's IEEE compliant. And these are the conditions for IEEE compliances. And what you see is that while you do calculations, there are errors which you cannot deal with. Like you do this multiplication, okay? What you obtain is this guy. Now this, it's outside your dynamic range. And you have to drop it, and what you do is you do rounding. You have to obtain this, because trying to obtain this means you have to increase the accuracy of the system, which you cannot do that. Now we will look, okay, I'll try to look on the main ingredients in floating point. I don't have much time left. And we'll look on how you do the operations and a bit on how things are getting out of control due to that kind of errors. Now, let us look at the addition. Because now the addition is actually a very unpleasant operation. It used to be a nice guy, and now it's getting a very nasty one. You know, I have two numbers and I want to add. In integers or in fixed point, I just have to add them because they are aligned. They are one under the other. I just take them, same position, add, carry, whatever. I do my best, and then I'm done. Now, if I want to add two numbers in floating point, I have a problem because they most likely are in different ranges. And I want to add apples with apples. Which means, first of all, I will have to align them. Aligning means that I will have to do some shifts and updates on the exponents in such a way that both numbers have the same exponent. Now, when they have the same exponent, the significants are aligned. And then I can do something. Addition, subtraction, or whatever I have to do. Now, I am doing that, and then the result may require some kind of post-calculation, because I may have to round, and then I have to normalize. In here we have an example, okay? Now we have two numbers, and then this is to a power 5 whatever, to a power 1 whatever. And I want to add them. In order to add them, I will have to align them. Then I will shift this guy. And then what you see is that now I have 4 bits which are outside of my range. I can drop them and say, okay, while I'm shifting them, I don't care. They go to the garbage bin. But maybe they can count. Now I will do the addition, and I will do it in the way that I keep everything. And now this is my result. Assuming that that was not an addition, maybe it was a subtraction. And if the subtraction result was like in here, I get 0.00 whatever, the normalization part will bring me those bits back. I have to normalize the result, right? Now I'm lucky because I don't have to do normalization. But if I would have done a subtraction and in here was the result, you know, 0.000, okay, then I would have to normalize until I get 1 point something here, and the bits which I shifted out of the calculation now will get back in the precision. That's one story. Then dropping them completely is not good. Might be good to save them. But now you see, I might shift the entire number. Can I keep it entirely? In the extreme case, yes?
Can I ask something?
No. Yes?
We only need 1 bit actually from next bit, right? For the rounding. Because if it's 0, you can, if it's 1, you can go to higher and add 1.
There are very many ways of doing rounding. It's not only that, but you see, I'm not talking about rounding. Here I have rounding.
Yeah.
What I'm saying, it's a different story. You know, I'm shifting in order to align, and some bits are out of the domain. After I obtain the result, they might be useful to bring them back. And the story is that if I do a shift, which is, you know, moving this completely out, I have to keep a lot of them, which is not really feasible. Now, in this case, what we have is we have this result, and there are those bits out. I can drop them, and I can say, this is the result. But if I look at those, they are not far away of being almost 1 unit in last position. Then I can get a better approximation of the result by saying, okay, this is like a 1 in here, then I will make now an addition, and this is my final result, which is closer to reality than when I drop the numbers. Now, what I see is that I did an addition, and now for that addition, what did I do? I had to shift, and then I have to do the addition, and then I have to do a rounding, which is actually another addition. And I have to shift, and I may have to update the exponents. Then a simple addition ends up in being a complicated stuff. Now, the accuracy can be controlled by rounding, but rounding actually means, you know, propagation of a carry. Propagation of the carry may require an extra shift because I may have to normalize again. You know, life is tough. My job is to get normalized numbers and to produce normalized numbers with a value which is as close as possible to reality. Now, multiplication is beautiful. When I do multiplication, I have very nice. I multiply the significance, I add the exponents, and then again, I will have to do maybe some kind of normalization. But the normalization will not be that bad because I'm starting with numbers between 1 and 2. Okay? All the discussion on division was for numbers between 0.5 and 1. In floating point, the story from the division can be applied if I change now the PD plots with a different dynamic range, which is from 1 to 2. All numbers are significant, are normalized, and they are 1 point something, but never 2. Now, if I do the division, division is just division of integers and subtraction of exponents. I may also need a normalization because I'm starting from 1 to 2, and I may get into 0.5 to 1. Overflow and underflow can occur all the time. Then I can check that. But you see, multiplication and division do not have that much overhead as addition. I can go for them straightforward. While for addition, I have to do preparation, and things are a bit more complicated. Now, I also have another operation, which is square root. And square root now can be solved. I need a unit which can do square root. That one is kind of similar with the divider. And I have to do some kind of normalization. I have to play a bit with the exponent. If the exponent is even, it's simple. I divide the exponent by 2, and then I compute the square root of the significant. If exponent is odd, I have to make it even, and then I do the job. Now, what we don't know in this is how to do this kind of, you know, thing. Maybe we'll get there next week. I have to make a schedule and see exactly what I'll tell you next week. Now, my time is up, unfortunately. Then next week, we'll finish the story, and on Wednesday, I'll publish the take-home exam. Remember? I assume you want it, right?